try it again.
Would you like
Hey,
to
buddy.
do something?
How's it
No,
going?
no, it's good.
I'm gonna talk anyway a little bit louder. Yeah. Working?
Well,
and please come and sit here. Front row is, I think, the only thing left. Okay, so can I start? Yes. Okay, so welcome to our last Science Cafe of 2018. And as we announced before, it's quite a special Science Cafe. Some of you have been here for the Interstellar movie, and we will continue with a talk about understanding Interstellar. The speaker of our Science Cafe is Dr. Guillermo García Pérez. Guille did his PhD in University of Barcelona. He works on complex networks, theory of complex networks, and now since less than a month, actually, he joined our Turku Quantum Technology Group in Turku as a postdoc. Well, Guille has a passion for public outreach, and he has been giving several public outreach talks, and in particular also this Interstellar talk is not the first, let's say, version. There have been several, mostly in Spanish, I guess. And so, well, it's a bit of a different Science Cafe talk because it will be a little bit longer. After the talk, that may last around 1 hour and 20 minutes, approximately, we will have a question and answer session with a panelist as well, Dr. Hiro Vilja from the University of Turku. So I think we are ready to begin. Guille?
Hello, everyone. Can you all hear me well? Even at the back, more or less? Okay. So, yeah, during this talk, what we will do is I will more or less start with the plot of the movie. So we will follow the plot, the story, and I will introduce the physics as it's presented to us, as it happens, let's say. But first of all, I would like to tell you a little bit how this movie was created, how it started. And it started with, so here you have Christopher Nolan, the director, and here you have Kip Thorne. Kip Thorne is a very well-known physicist. Actually, he is a Nobel. He was awarded a Nobel Prize in last year because of the discovery of gravitational waves, the detection of gravitational waves. And he was the one who started the project. Really, the first script of the movie was actually written by him, and somehow it arrived to Jonathan Nolan, which is Christopher Nolan's brother. And he got really interested in the topic. He started studying physics and changing the script until it became what it is now. And during the whole movie, it's not that Kip Thorne was just an advisor. I mean, he was really, in some sense, he was like a scientific policeman. So he was trying to avoid the Nolan brothers taking the physics a bit too far, let's say. And at the same time, he calculated everything. So everything we see is very well calculated, and even the visual representations that we see in the movie are very realistic as well. Not fully, because there are some simplifications, but they are very, very realistic, which makes it very interesting. And also, if you are interested in science, Kip Thorne wrote this book, which is The Science of Interstellar, which basically explains all the physics and everything you need to understand the movie, but also to learn a lot about physics. It's very well written. I really recommend it, and it's a basic level. It doesn't require any previous knowledge at all. Okay, so I guess we can start. So the movie starts with in this maybe not too distant future, in which humankind is facing this very terrible condition. There is this blight that is killing all the crops, and well, the story, the reason why the movie is in this scenario, it starts in this scenario, is that basically Kip Thorne needed some sort of scenario in which humankind was not, it was not post-apocalyptic, it was more of a pre-apocalyptic scenario in which humankind needed to leave Earth in order to survive. So he didn't really know what to do, what a realistic scenario could be. So he organized this sort of events with like dinners and with biologists and experts on the topic, and they discussed about a possible situation for this to happen, and they arrived to the conclusion that it was kind of realistic. This could happen if there was like a blight that that eats chlorophyll in all plants. It could be really a catastrophic situation like this one. And actually, it's very interesting to see that. Do you remember at the beginning of the movie there are like witnesses saying how tough life was, that they had to turn the plates over to avoid the dust getting in and so on. Those are actually real people that experienced a dust bowl in the 1930s. And in America, this was, in some regions of America, this was more or less the situation. And those are real witnesses. So we would say it's a realistic scenario. So what goes on is that, well, we are presented the characters, and we see that there are some weird things that start to happen. There is the ghost, but there's also the GPS that starts not really working. So they take this GPS device from the drone, and they put it into these machines, these harvesting machines, and the GPS is not really working well, and that's also related to these gravitational anomalies that we see. Later on, I can tell you what's the connection between gravity and GPS, but it's part of the same thing. And then they observe these lines on the floor, that they realize that they are in binary code, binary base. They are the coordinates of somewhere. So they go to the place, and it turns out that it's a secret NASA base, in which they are presented like the whole situation, what the plan of NASA is. Actually, there's two plans. But they tell them that there is a wormhole that someone has put there. That it's not a natural thing to happen, but there's been, for like 50 years, there's been a wormhole near Saturn. And, well, they are presented the two plans, right? There's plan A and plan B. Plan A is, okay, you get your spaceship, you go through the wormhole, you find the nice planet on the other side, and then in the meantime, the professor says, I will solve this equation that will allow us to control the gravitational field on Earth. So we can shut down the Earth's gravitational field once we know that, and we can lift off Earth everyone, and we can save humankind. In case this doesn't happen, there is plan B, which is basically that you're going to take with you on your spaceship, you're going to take these fertilized eggs, human eggs, and then you can help humankind to survive. I mean, everyone you know is going to die, but there's going to be other humans, so the species will survive. Okay, but now we can start talking about physics. What is a wormhole? Well, if I am to explain you a little bit what that is, I need to introduce first general relativity, which is the main theory in this movie. It's actually a field of research of Kip Thorne, and it's what's driving the movie mostly. So this is our current theory for gravity. And it started with this man that I'm sure you all recognize. This is Albert Einstein. And he proposed this theory in 1915. And actually, it started 10 years before, in 1905, when he proposed the special theory of relativity. That it doesn't explain gravity yet, but it's a very interesting theory that basically has two postulates. The first postulate says that all inertial frames of reference are equivalent. Okay, so what's a frame of reference, first of all? Well, a frame of reference is whatever I use to refer to points in space and time. So if I am to understand my environment, if I am to perform any sort of experiment around me, I need to have some sort of device, some system to refer to points in space and in time as well. So this could be, for example, a set of rulers that I could have, like, say, imagine I have a ruler in this direction, another one in this direction, and another one pointing up. And I refer to this point as the point that's laying a meter to my right, 1 meter in front of me, and say 1.5 meters in the up direction. And that uniquely identifies a point. That is a reference frame. And I could have the same with clocks. I could also refer to the points in time. What we are considering frames of reference that are inertial. That means that they are not accelerating. So if I observe an object in my reference frame upon which there are no forces acting, so there's no forces acting on it, it shouldn't accelerate. I would observe that body either in rest or at constant speed, moving in a rectilinear motion. That is inertial. So for us, it's basically just, we would say, like standing still or moving without acceleration. So what this postulate that seems quite innocent is telling us actually is that all reference frames or initial reference frames are equivalent. This means the following. Suppose that we now are floating in space and from your perspective you're standing still, you're not moving, and I start moving, like I kick the wall and I start moving with constant speed in this direction. Now the question of who's moving for you is going to be obvious. You are standing still and I am the one moving. That seems obvious. But from my perspective, I am standing still and you are moving in that direction. And who's right? Well, this postulate says that we both are. Both answers are as valid as the other. So with this postulate, Einstein removed the idea of absolute motion. There is no such thing as standing still. It's only standing still with respect to something. Now the second postulate says that the speed of light is independent of the state of motion of the emitting source or body. This means that if I, so as you know, if I take a light bulb and I light it up, the light emerges from the light bulb and propagates, and it doesn't do that at infinite speed. Light propagates at a finite speed, which has been measured, which is very well known. It's about 300,000 kilometers per second. But what this postulate is telling us is that velocity does not depend on whether the light bulb is moving or is standing still with respect to us. And this is really counterintuitive. Here you can see a situation, like a thought experiment that we can do, in which you will see how counterintuitive this is. So suppose that I am on this rocket, and you are on Earth, as you really are, and I take a laser beam like this. Well, sorry, I am moving towards Earth at a velocity that is half 0.5 c. C is the speed of light. It's this 300,000 kilometers per second that I mentioned. And what the postulate says is that if I now take, from my spaceship, I take this laser beam and I point it towards you, towards Earth, you're going to see this little red point moving at a given speed, which is the speed of light. And if you measure that speed, it's going to be this 300,000 kilometers per second. Now, I'm moving towards you at 150 kilometers per second, 1,000 kilometers per second. And yet, if I measure the speed of that same red dot, I observe the same one, which is completely counterintuitive. This is not how we think about motion. If I now told you that I'm moving, like with a car here, in this direction at 10 kilometers per hour, and a fly inside my car is moving at 10 kilometers per hour with respect to me, it wouldn't surprise you that if I told you that you see the fly moving at 20 kilometers per hour. The velocities are just added. This is how we think about motion. But this does not happen with light. For light, we would all agree on the same speed. We will observe the same speed. And now you're probably thinking, okay, this is impossible. If you are moving, there's no way we can observe the same velocity. There's something wrong there. And it really is. What's wrong here is our intuition, which is based on wrong assumptions. The wrong assumptions are that we think that space and time are the same for both of us. That an hour in my clock is equivalent to an hour in your clock. And that a meter in my ruler system is equivalent to a meter in your ruler system. But this is not the case. This is one of the conclusions that we can draw out of special relativity. That when I move, as I move, you observe that my rulers are contracted, and also that a clock in my reference frame ticks slower. So therefore, this is consistent. It can happen that it actually does. It happens that both agree on the same velocity, because the rulers and the clocks are not equivalent, we would say. Okay, but this is a very shocking theory that he proposed like over 100 years ago, but yet he wasn't completely happy with it, because this theory that he proposed was consistent with the theory of electromagnetism that was already known at the time, but it wasn't with gravity. And why is that? Sorry. Yeah, I forgot to mention that until special relativity, we conceived space and time as two different objects, but we now think about them as a single entity, which is space-time. How I move in space changes how I move in time as well, how time passes for me. Okay, but going back to what's wrong with gravity and special relativity, the thing is that the theory of gravitation that was known at the time was Newton's gravity. And it says that if we take two masses that are at a given distance r, there is an attraction between them, a force pulling them together, by an amount that it's proportional to the product of these two masses, and that decreases with the square of the distance between them. But now the question is, suppose that now you take, for example, the blue mass. I give it to you, and I keep the green mass for me, and I move very far away, and you are measuring from your lab, you're measuring the strength of this force. So how much my blue mass, my green mass is pulling your blue mass. And now at a given time, I just take my green mass and I move it a little bit backwards. So I increase this R. If I increase this R, the strength of this force should decrease. But how much time does it happen until you can notice that difference in the force? Well, according to Newton's law of gravitation, this should be immediate. There should be no time, no delay until this is observed. But this is completely inconsistent with special relativity. Because in special relativity, if there's something that can travel, even if it's information, something that can travel faster than light, we could devise experiments in which we violate causality. That means that we could come up with an experiment in which the cause happens before the effect. So this is something that we are not, in general, ready to believe. So we don't accept that things can forward, can move faster than light. So he kept thinking for many years how to solve this, and he had what he called afterwards the happiest idea of his life, which is the equivalence principle that I will not explain. But with that and a lot of hard work, 10 years later, he came up with general relativity. And in this theory, he generalized special relativity by allowing this space-time that I mentioned to warp. So what general relativity says is that mass and energy is the same thing, warp space-time. This is how we conceive nowadays gravity. And I'll tell you right now a little bit more about this. So what the theory proposes is that space-time is not something flat, but it's something that can be curved or warped. And I will use an analogy for you to understand how this works. So suppose that now we take an apple. This is actually from the gravitation book by Kip Thorne as well. So we take an apple, and now this apple is going to represent space-time. And now imagine that you are little ants, or some very tiny beings that live on the surface of this apple. And for you, because you are very, very small as compared to this apple, you don't realize that the apple is actually curved. For you, you only see a very tiny region of it. It's like as we see Earth, actually. This is what happens to us in Earth. We cannot see that there is some curvature. It really looks flat. So in this flat, almost flat space in which you always observe, in which you live, you never turn. You always go in the straightest possible line. You never take any turns. Okay? Well, then in the apple, it's evident you cannot draw a straight line because the apple is not flat. But you can draw the straightest possible lines, which are called geodesics. These lines that you see here. Now, the thing is, as you imagine that you're one of these ants, and as you approach this stalk, this little thing in the apple, the apple around it is highly curved. And what's going to happen is that this straightest possible path that you're following is going to be bent towards this stalk. So from your perspective, you don't realize that the apple is curved at all. From your perspective, it looks flat. But what you notice is that even if you didn't choose to turn towards this stalk, you're going to be driven to it. But it's just an apparent force. The stalk is not really pulling you towards it. It's just that the space around it is curved in such a way that the straightest possible lines tend to go there. So this is the analogy. So this is how general relativity conceives gravity nowadays. If this is space-time, we're actually beings that move in the straightest possible lines in space-time. So we're moving in time as well. Now we are all moving in time. And our trajectories in space-time are curved because the space-time is bent around massive objects. Okay, so how does general relativity look like on paper? This is just for you to more or less know how we understand this mathematically. So these are the Einstein equations, field equations, and there are here. These are simply some constants. This is 8 pi. This is the gravitational constant. This is the speed of light, and this is the cosmological constant. They're just constant numbers. Now, this is the stress energy tensor. This is the mathematical object that encodes where is the mass or the energy in the spacetime. So this would be where is the stalk in the apple. And these equations, in these equations, this left-hand side is telling us this is related to the shape of the apple. So when we solve them, once we know where the energy and the mass are in our spacetime, we solve these, and then we know what shape does the apple or the spacetime have, and then we know everything, because we know how to move in this spacetime. It's just following the straightest possible lines. So this is just for you to have a little idea of how this looks like. Okay, so now we can move on, and we can now, I think we can now talk about wormholes, what they are. So a wormhole is basically, it's like a, well, it's a very recurrent idea in science fiction. It's like a portal that takes somewhere else in a very short time. So in this representation that we have of space-time, it would be something like this. So this surface now, this is actually very similar to what we've seen in the movie. The ones that have seen the movie right now, this is more or less what they presented to us. So this is now a slice of space-time. But be aware that this is not, space-time has a time dimension. It's 3 space dimensions and 1 temporal dimension. Here we're only plotting 2 space dimensions. So this represents space-time at a given time, let's say, a given coordinate time, and say without changing the height, just what happens in this plane. And the idea is that if you take, imagine these 2 distant points, these 2 are really distant in space-time, because we live in this surface, so we cannot move in the perpendicular. This doesn't have any meaning to us. If you want to go from A to B, you need to take the long run, in principle, unless you have this object here, which is the wormhole. And this wormhole, which is this sort of warping of the space-time, is a possible solution of the Einstein field equations. So this is allowed by the theory. It's not really science fiction in that respect. These are known solutions. The problem is that the energy that you need in order to create one of these must be negative. And this is something we don't know. I mean, we don't have. We cannot just do this. So this is why in the movie they say someone has put the wormhole there, because this doesn't happen. Naturally, it would be unstable. This wouldn't. We wouldn't observe that. Okay, but then they talk a little bit in the movie as well. How does this look like to us? I mean, from the picture we might think, okay, it's like a kind of a black hole in the middle, but it doesn't. It's not, because we would be on the surface only. So we cannot see the hole in the middle. All we see, everything that happens in our world, is what happens in this surface. So how does a wormhole look? In the picture, in the movie, we've seen that it looks like something like this, like a kind of crystal ball. And they tell us in the movie, okay, what you're seeing when you look at the wormhole is whatever is going on the other side. So light travels from the other side and reaches you. But why this sort of effect? This is very different from, I don't know, saying how I see a room from the door. Like, then I don't see any sort of bending like this, any sort of like lensing effect. Where does this lensing effect come from? Well, as I said, things move in space-time when no forces act upon them, propagate in space-time following the straightest possible lines, this geodesics. So now suppose that we have, like we're here on Earth, and there is a very distant galaxy, like this one, and in between us, between both, there is this cluster of galaxies. So there's many galaxies there. Of course, if we look in the direction of this galaxy, we cannot see it, because it's behind these galaxies here. But this galaxy is not just emitting light towards us, it's emitting light in all directions. So it's actually emitting light in this direction, for example, but now the space-time in between both is bent, is curved because of the mass of this galaxy cluster. So the trajectory of these light rays are bent as well, and they eventually reach Earth. But they reach Earth from the left, we would say, not from a straight line. So if we look a little bit to the left, so if we look in front of us, we see the cluster, the cluster of galaxies. But if we look a little bit to the left, then we see this blue light coming from the galaxy. And if we look instead a little bit to the right, we see the same effect because it's symmetric. And the same happens if we look a little bit up, a little bit down. So this happens around this galaxy cluster. So in this situation, we would see this, the galaxy cluster, and in a very distorted manner, the galaxy behind it. So this is what the theory predicts. And this is actually a picture taken by the Hubble telescope. So this is something that we observe. This is a prediction from the theory that has been confirmed. So now if we go back to the wormhole, now we can understand that if I am here and I look through the wormhole, look towards it, I'm seeing the light that comes from the other side. But because this is distorted, I don't see light traveling in like a straight line as I see when I look through a door. That there is no distortion. Here the paths are curved, and therefore I see this gravitational lensing effect. There is a very, very interesting story, I think, I like it a lot, about the movie and the thing with the wormhole. This is a very interesting question, which is, how was the wormhole detected in the first place? I mean, it's a very tiny object. It's like a couple of kilometers wide, and it's near Saturn, and it's not emitting its own light, just the light that comes from the other side, but it's not bright. And it doesn't have much of a gravitational pull. It has just a little bit of it. So it's not it's not obvious how do you detect that. In the original script that Kip Thorne wrote, so Kip Thorne has been working in this LIGO project, which is the gravitational detection of gravitational waves. And he had the idea that, so if Earth is here on B, and this is the system where Gargan 2I is, and all these, there's all the black holes, as I'll tell you later. He had the idea that maybe in this other far distant galaxy, there could be a collision between two black holes that could create, or would create, gravitational waves. So in space-time can be warped in such a way that waves are propagated. And he thought, okay, then the waves would go through the wormhole, and they would, in our system, in our solar system, the wormhole would act as a source of gravitational waves. And at LIGO, at my place where I work, he thought, they would be detected. And we can triangulate the system, the signal, and look where it came from. And then we would see that it comes from Saturn, which makes no sense, and then we would detect that there's actually a wormhole there, and gravitational waves come from it. But this was discarded in the final movie because it was a bit too complicated. But I think it's a pity, because this was the movie is from 2014, and a couple of years later they were actually detected for the first time. So it would have been very nice that it was included in the original movie. Okay, so going back to the movie. So now they accept the mission. They say, okay, yeah, if plan A is a possibility, I want to save my kids, I want to save my family, I'm going there. So they all get into the Endurance and with the Rangers, and they approach these. They approach the wormhole. They go through it, and then they arrive to the distant galaxy. By the way, do you think it's realistic, this thing that happens when they go through the wormhole? That everything starts, it's very shaky, and there is this kind of cool effect on the walls. Do you think this is a realistic thing? Well, what's your bet?
It doesn't bend the space-time, so I bet it would have some kind of distortion that wouldn't be uniformly.
Yeah.
So
Maybe. But the thing is that this is a funny thing about the movie, is that, as I said, Kip Thorne calculated everything. So he actually calculated how the wormhole is and so on. And then what he did all the time is he calculated things in Mathematica. And actually, then he gave this mathematic code to the people from the special effects unit. And they would make the nice, cool video. And then he did that for the wormhole. And he got a call from Christopher Nolan saying, Kip, we have a problem. And then he went to his place, and he showed the video. And the video was simply like, okay, we are approaching the wormhole. We have passed the wormhole. And Christopher Nolan was like, passing a wormhole, it should be a little bit more exciting. So then they added all that. But literally, I mean, it's just a piece of space-time, like the one we live in. So it shouldn't be, it could be that maybe if the gravitational pull was too far, but not in this kind of wormhole. You shouldn't even notice any force or anything, you just pass inertially.
what about the angle that they approached it?
Yeah, that's because, well, the wormhole that they have is the kind of Ellis wormhole that in principle should have no gravitational pull, so you can stand still in front of it and yet you do not attract it. But Christopher Nolan wanted a kind of nice effect, so Kip Thorne modified a little bit, so everything is very calculated. He modified a little bit the wormhole so that it had a tiny gravitational pull, so they could orbit around it and make this cool scene. Okay, so then they pass through the wormhole, they arrive to the distant galaxy, and they find that there's 3 planets that could be potentially inhabitable, and then there is also the black hole. So here's where things start to get a little bit weirder, let's say, and I think this is the right time to introduce what a black hole is. So as you, sorry, wait, okay. So what is a black hole? Well, as they explain in the movie, a black hole is a region in which gravitation is so strong that not even light can leave from it. But so in this representation that I've been using before of this kind of sheet that is distorted or warped, it would look a little bit like something like this. And the thing is, at some level, there should be what is called an event horizon. So this line in this case, that once you pass it, you cannot come back. Not even light can come back, can get back from it. But why is that? Okay, this is where the talk gets a little bit. Perhaps this is the most technical part of the talk. So just I need your attention. So this that you see, what you see here now is this is a space-time diagram. So what am I showing? What am I showing here now? Okay, suppose that I brought my own black hole, and I have a little black hole that I place here, and it's standing still. And now we're going to study what happens in the line that joins my outside with the center of the black hole, let's say. So we're going to study what happens and how things move on that line. Okay? And this is going to be represented by this dimension here. This space dimension that we have here is the coordinates of these lines. So, for example, if where I am would be this point, midpoint between me and the black hole would be this thing, and then there is the event horizon, and beyond the event horizon, everything is colored in black, but it's inside the black hole, let's say. But we want to study how things move. So now we are plotting also time. And the way we are plotting time is in the vertical direction. So this would be me now, and this would be if I'm not moving with respect to the black hole, this is me in a couple of seconds, let's say, a little bit later. Okay, this is time. And now, what are these blue lines here? These are the trajectories of light. So if I'm standing here, like right here, and now I light my my laser outwards in the opposite direction, still in the same line, but in the opposite direction to where the black hole is, if I do this, then this red point is propagating at a given speed, which is the speed of light, but the trajectory that it's going to follow is this blue line. So it's moving away from the black hole, and this arrow here represents the velocity. So in this amount of time, it's covered this amount of space, we would say. This other line, almost perpendicular to it, it's the opposite case. It's a case in which I light it towards the black hole. So obviously it moves towards the black hole, and eventually it would get in like up here. Okay? Now, what are these kind of wavy lines in the middle? This is me, because as I told you, relativity prohibits anything moving faster than light. So if I'm here and I like this, there's the two lines because I'm lighting two lasers, one in each direction. I am never going to be able to cut those red lines. I'm not ever going to be able to pass them. So everything I do, never mind what I try and never mind what I do, I will always be within in the space or in this region of space-time given by these two lines. I'm never going to be able to leave these two. If I wanted to reach this point, I would have to cover this distance in a time that is less than the light needs to reach it. So I cannot do that. So this is my future light cone. Okay? But now, what happens if we repeat the same thing a little bit closer to the event horizon? Then you see now that these lines are a little bit bent, and then now the light that I emit towards the black hole is more or less the same, but the light coming out of it has a little bit more difficulties to do so. So in a time that is now larger than this was, it covers a little bit less space, let's say. So it finds it increasingly more difficult to leave the black hole, but still, yet it does. But if we do this now inside the event horizon, once we've passed the event horizon, the light moving towards it is moving as expected towards it, but the light that I light outside of it, in the let's say towards the outside of it, is still moving inwards. It's doing it slower. I mean, it's not falling towards a black hole that fast, but it's still falling towards a black hole. And still, it applies that everything that I can do is within these two arrows, within these two lines. My future is still here, in this area here. But now look, that there's no way that I can go out. So my future is necessarily pointing towards the inside of the black hole. So this is why many authors like to say that inside the black hole, the radial coordinate, this coordinate that we were talking, the space coordinate, has now become a time coordinate, and also that the center of the black hole is not a point in space, but it's a moment in time, because it's impossible to avoid it. Just like it's impossible for us to avoid the time in an hour. I mean, it's going to happen, and the same thing applies here. Never mind what you do, it's going to happen that you reach the center of the black hole. And at the center of the black hole, it is believed that there is a singularity, which is where the theory becomes a little bit, it breaks down in a way, and we'll get to that later. But okay, from this discussion, we might expect that a black hole is just like a black ball, and that's it. But in the movie, we see something that's little bit different. We see this thing. Now, what's going on here? What is this? So, well, the black hole itself would be this thing in the middle, the center. But what is this kind of yellowish thing around it? This is called an accretion disk. What's going on here is that, well, black holes are not isolated beings in space. Usually they interact with other bodies, like for example with stars, and they might absorb a star. And they can orbit together, and eventually it might happen that the star happens to be absorbed by the black hole eventually. But it doesn't do it like in a straight line, like just in a moment. It takes time, and they orbit together, and slowly the star becomes flatter, and it becomes like the orbit becomes closer to the black hole, and it forms a disk, a very hot disk. This is a star that is highly compressed, and it even creates some jets of very energetic particles living in the two directions. But in here we don't see it because this is a very, very old black hole. So it has cooled down, and now the temperature of this accretion disk that we see here is more or less the temperature of the sun. So this is why it's also very nice for us to go and live there. But there is one more thing, and it's okay, this is a disk, but what is this thing around it? Does anybody have a clue? Okay. Do you remember what I told you about the light bending the trajectories because the space-time is warped? So this is actually, what we're seeing is this, basically. So we have the black hole, we have the accretion disk, and we are here. And of course, the accretion disk is emitting light in all directions, but the light emitted towards the black hole is absorbed. We don't see that one. But there is light going upwards, and that light is bent, and we eventually see it. And it's also emitting light downwards, and that light we also observe. So we're actually seeing the back of the accretion disk. Here you can see it more clearer. This is the FX people from the movie substituted the accretion disk by this kind of colorful thing, so it's easier to identify which part is which. So the back of it, this part, is what we see here. And here. This is from below. Okay? Now, you can also see here that the black hole here looks asymmetric. It's not symmetric, but in the movie, it doesn't appear to be so. This is another of the simplifications that the black hole has been through. This is actually because as I'll tell you later, this black hole needs to be a rotating black hole. And then you don't see, if you look at a rotating black hole, you don't see it as symmetric because the light that trajectories of light that come from the left of it and the ones coming from the right of it, they're not equivalent. So you would see this sort of distortion. And there is a further simplification that doesn't appear in the movie, and it's that we wouldn't see the accretion disk, all of it, the same color. We would see the accretion disk is matter that is rotating at very, very high speeds, relativistic speeds, comparable to the speed of light. So this side of it is matter that is coming towards us, and this side of it is light that is moving away from us at relativistic speeds. So then there is the so-called Doppler effect, which is the same as we hear when we hear the noise coming from a moving source. In this side, it would be a little bit more bluish, and in this side, it would be red. But this is a simplification that they didn't include in the movie either. Okay, and now, Now what's going on in the movie? So they arrive to this, there is a black hole, and there is the 3 planets. There is Miller, there is also the Mann's planet and Edmund's planet. And they decide to go first to Miller's planet. And then they go there, and they find this unpleasant surprise that there are these very high waves that get them trapped there for a few hours. And then when they come back, there's been like 23 years on Earth and also in the Endurance spaceship. But okay, this raises at least 2 questions. First of all, what's going on here with the waves? Why the waves? And also, what happens with time? Why is this? What is this temporal distortion that we see? Well, let's go first to see what this effect that is very important in black holes, especially, which is spaghettification. This is called so because basically, if you fall into a very, very strong gravitational field, you might be spaghettified. You might be stretched in the direction in which you fall and squeezed in the perpendicular. This is easy to see in this picture. Here you have a planet, and you get 2 masses, these 4 masses forming this sort of square here. And the thing is that objects don't fall vertically. They fall radially. They fall to the center of the planet. So the arrows showing the direction of the falling, they're not parallel. They point a little bit inwards. And also, this mass here, because it's closer to the center of the planet, is falling faster than this one. So it's stretched in this, it's elongated, as they say here. Okay, but if we think about, for example, the system Earth and Moon, the Earth is actually falling towards the Moon. It's feeling the gravitational pull of the Moon. And so it's, in a way, it's spaghettified as well. So it's stretched from the sides, and it's squeezed from the sides and stretched in this direction. So this is what creates a tide. This was already discovered by Newton very long ago. But what the interpretation that they have for the waves in the movie is that near the black hole, the Miller's planet is orbiting very close to the black hole. And then the pull is so high, it's so strong, that it's actually deforming the planet itself, like the ground. And it creates these earthquakes underwater, which create these tsunamis periodically. So that's why there are these very, very, very high, very tall, very high waves. But what happens with time? Well, this is a representation again of a black hole, but this time this is Gargantua. This is the black hole of the movie. And here you can see the level of detail that was put on this. So there are 2 additional black holes here that don't appear in the movie. At some point, Cooper mentions, I can sling around this neutron star. Well, it shouldn't be a neutron star, according to Kip Thorne. It needed to be black hole. So in his calculations, he included these 2 extra black holes that were used for the spaceship to move. We will see that later, how that works later. And there is Miller planet. And here you see also the colors. What are the colors? Well, as I said before, this is a space-time. It's not only space, but all the time I was representing space because time is very difficult to draw. But here, you see the colors represent this distortion effect, this time dilation. So one of the very well-known effects of general relativity is that near a massive body, clocks tick slower. So this is actually what we see in the movie. So here, Miller's planet is so close to the event horizon that time here ticks slower, much, much slower. And there is this effect of 1 hour there is equivalent to 7 hours in, like here in the Endurance, very far away, or on Earth, it's the same. Because when you're far enough from the event horizon, this effect is not really important. And you also see here, there's the thing with the spin and the thing I mentioned about the black hole being a rotating black hole. Well, this is a kind of an anecdote as well, which is that when they were talking about the movie, Christopher Nolan said at some point, okay, I want it to be like this, 1 hour on the planet, 7 years on Earth. And Kip Thorne said, no, this is not possible. I mean, you cannot have a planet, like Miller's planet, orbiting that close to a black hole, because then the orbit would be unstable. There is no way that can happen. So if the orbit of the planet is to be stable, the largest effect that you can have is 1 hour in the planet, 1 hour and a half on Earth, which is not very dramatic. So Christopher Nolan said, well, I don't care. There must be a way. Go and think. And Kip Thorne said, no, I mean, I know what I'm talking about, and it's not possible. Go home and think. Okay, so he went home, and then he thought, okay, there's no reason why it should be a non-rotating black hole. If it's a rotating black hole, the closest orbit to the closest stable orbit to the event horizon can be that strong. And this is why the Gargantua needs to be a rotating black hole. And there's also a few more things which might be important. Here you see spaghettification and this loss of information and these weird shapes here. This is because they assume the black hole to be like the singularity that is at the center of the black hole in the inside. They assume it to be something that they call a BKL singularity, which is a chaotic singularity. This is something that as you approach these forces, this spaghettification becomes very chaotic in all directions. So it breaks down everything. But for the plot, it's very important that they pass through a singularity. That I will tell you later. But here you can see that there is some other singularities at the very beginning of this. These extra singularities are what they call gentle singularities. They mentioned that in the movie. Those gentle singularities were actually proposed, I think, for the first time in 2012. So this is actually using physics that's quite up to date, let's see. Okay, so now we know what's going on with the waves and with time. And, well, during those 23 years that they spend in a few hours in Miller's planet, when they come back, a lot of things had happened. Specifically, Professor Brand is about to die, and then he confesses that everything Plan A was a scam right from the start. That there was no way that Plan A could be really happening, because to solve the equation, this equation that would allow to deactivate gravity, he would need the information, the quantum information, from a singularity. And that is impossible, because if you might get into a black hole and get it, but there's no way that you can get it back to Professor Brand. So he knew that it was a scam, but he wanted people yet to go on the mission, because he wanted Plan B to be realized. Okay. In the meantime, they go to Man's planet to save Matt Damon, and Matt Damon seems to be not a very nice guy, and he didn't want to die alone. And basically, he was fooling also people. This is like the betrayal part of the movie. Everyone is very bad, and he's fooling everyone because he wants to get back to Earth. So he takes the Ranger. He tries to dock to the Endurance spaceship, but he cannot because he doesn't know the protocol, and he's not allowed. And he breaks the spaceship, and then Cooper, in a very thrilling scene, he gets back control of it. But the problem is that now the Endurance has been severely damaged, and it doesn't have enough fuel, no oxygen, and so on, to get back to Earth or to Edmund's planet, in principle. But then Cooper says, okay, we can just, we have nothing to lose. We can just use the black hole to get some extra energy, we would say, and get to Edmund's planet. Because we have nothing to lose, let's just try it. It's crazy, but let's try it. What does that mean? So this is what we would call a gravitationally assisted maneuver. Here I'm going to show you a video of how the Juno mission was sent to Jupiter. This is like a simulation of it. And you will see that the aim is to go from Earth to Jupiter, but the trajectory is going to be a little bit unexpected. So in the beginning, it's launched, and it's not accelerating. This is inertial. This is for free. No fuel is being consumed. But now, at some point, there is this deep space maneuvers in which Juno accelerates a little bit to change the trajectory, and then it's falling back to Earth for that extra kick, and then it passes really close by, like 500 kilometers, and then with that extra energy is able to go all the way to Jupiter. So these things are really used, and this is what they use also with him. He talks about these using the neutron star to get to Miller's planet. This is the kind of things that they're talking about. In the case of the black hole, it would be slightly different because the black hole is not really moving much around the center of mass of the system. But it's this is the idea. So they decide to go for it, and then they pass very close to the event horizon, and that is when they say, okay, this is going to cost us another 50 or 51 years. This is because they are passing, now if we go back to this one, they are passing really, really close to the event horizon. So even if they spend very little time there, it's going to be a lot of years on Earth. So they do, they pass by, and at some point, the plan was, okay, we send the robot inside the black hole. Why? Well, because it's just a robot, and also because during those 20 years that the poor guy has been in the Endurance orbiting the black hole, he's had time to modify the robot to take the measurements. So it might be still possible, okay, we don't know. If we throw the robot in, maybe he's able to get the measurements and somehow get them out. We have nothing to lose. So that was the plan, and also because then they get rid of a little bit of mass, and then they have like an extra kick to leave the black hole. But then Cooper also decides to get inside the black hole with him, and when he does, this very weird thing happens, and he arrives to this, like, I don't know how to call it. This actually it's called the tesseract. They call it the tesseract. So what's going on here? Of course, this last part of the movie is highly speculative. And this movie has a maxim of, okay, let's try not to violate any known laws of physics, but let's also speculate because it's a movie. And let's speculate only on things that we know that we don't know. So there's things that physics does not yet know. So let's speculate on those areas. And this is what they are trying to do here. So what's going on here is based on the existence of a fifth dimension. Where does this come from? Well, so I'm sure you've all heard of string theory. String theory is a theory proposed to unify both general relativity, which is gravity, and quantum mechanics. And the idea is that instead of assuming particles to be point-like, which would interact in this way, this would represent two particles that interact and form a new particle. Instead now, they would be a piece of string, a little piece of string that might be closed or open, and two such strings can move together and then interact and form a new particle like this. And then they form this kind of surface, and it has its own action and so on. But this is how string theory is conceived, the quantum gravity. But the thing is, if you take this theory and you want to quantize it, you want to make it quantum, then it does work, but only if the number of dimensions is not the same as we observe. You need, depending on the theory, you need 11, 26 dimensions, a high number of dimensions. And this raises a question, which is, where are they? We clearly live in a three-dimensional world with one extra temporal dimension. But where are these other dimensions if there are really 26? And to answer, in order to sort this out, they proposed that these extra dimensions can be extremely small. They can be really curled up. Like, imagine a wire that is actually two-dimensional, right? Because you have the direction of the wire, let's say, but also in the perpendicular, you can also turn around the wire. If you are very small, if you're a little ant in that wire, you really notice that there's two dimensions. You can move along or also around it. But if you see that wire from very, very far away, you don't even notice this extra dimension. For you, it's just one-dimensional. The macroscopic dimension is a long one, let's say. So they propose that maybe there's extra dimensions that are curled up in some strange manifolds that are called, for example, Calabi-Yau's, which are very, mathematically very complicated, and there's many of them, and it's not clear which one should be the correct one for our physics, because depending on which one you take, you have different physics. But there's been a lot of research in that direction, and at some point, there was the idea that maybe there could be one of these extra dimensions could be microscopic as well, like the ones that we observe. And that yet it could be, let's say, consistent with what we observe. So the movie is actually happening in a situation like this one. So here you see the word brain. This brain is actually our universe. So now there's been a further simplification. Now our three-dimensional space is represented as a b-dimensional surface. So now we live in a flat, sorry, not flat, just two-dimensional brain, which is this thing. But there is an extra dimension which is perpendicular to it, which is this one, that we cannot see because all we see is contained in this plane. But the movie assumes that there is this extra dimension, and there is so for this to be possible, there must be this, what is called anti-de Sitter curvature. So this is like highly curved. So this space-time is highly curved in this direction. This means that, suppose that we are now, this is 10 billion light years. So this is the distance, this distance is, well, it's the time that it takes light to traverse from this point to this point is 10 billion years. So it's really a long distance. But if you move now perpendicular to the brain in this direction, from here, and I move from here perpendicular to this direction like this, and we cover just 1.5 centimeters, both of us, then the distance separating us in here is 1 astronomical unit, which is the distance from here to the sun. So it's much smaller. So this is some model of a string theory that could be possible, let's say. And the movie is happening here. So what's going on? So the beings of the bulk that they mention all the time, the beings of the bulk, that in the end of the movie they realize, or Cooper realizes that it's actually us. It's humans in the future that know enough physics to control all of this. It's easy for us in the future to leave this brain and live in the extra dimensions, and to form here a wormhole between this point and this point, as they do in the movie. And what happens is that Cooper falls into this black hole here. He passes through these singularities that I told you, these gentle singularities, and he takes the measurements that were required with the help of the robot of TARS. And then, okay, now he's got the info, he's got the data, but he's inside the black hole, and he needs to get it back to the daughter. So the beings in the bulk now help him, take him out of the wormhole, of the black hole. But of course you cannot do it in the brain because this is impossible, but you can do it in perpendicular to it. So the idea is that they take him, they pick him up here, they move him up, now they cover this distance in a very short time, and then they put him back on Earth. Okay? But there is a detail here, which is that now in this representation, Cooper, which is here, would be a two-dimensional being. And you cannot just take a two-dimensional being and put him in three-dimensional space that easily. So he needs to be placed always in a two-dimensional, in this representation, in a two-dimensional container, let's say. So what they propose is that these higher dimensional beings put Cooper in the face of a cube, which is two-dimensional, despite the cube is actually three-dimensional. And then they take this cube up, move the cube up, move all the way here, and then they put him back to Earth, like this. But when they do so, the opposite face of this one to Cooper, the other face, is placed intersecting the room of the girl. This is the interpretation that they give. So it's something like this. Now, the idea is that all that is fields, like electromagnetic fields, everything that is not gravity, is propagating only in the brain, which is this plane, and along the faces of the cube. So the light that is leaving Murph in this direction goes through this face as well and reaches Cooper on his right. So when he looks to his right, he's actually seeing Murph from the front now. When he looks to the left, he's seeing the light that's coming from backwards from her, and so on. When he looks up, he sees it from above, and so on. But this is if our world was two-dimensional. We can play a little bit and think of how this would look like if we consider this in actually this being three-dimensional. So how can we think of a cube that has 4 dimensions? Well, to construct a cube, we can take first a point, construct a line, and now move the line perpendicular to itself to form a square. Now move the square perpendicular to itself to form a cube, And if we could now move the cube perpendicular to itself, we would have this 4-dimensional cube or tesseract. And every face would be a cube, although we cannot represent it. Why not? Well, imagine now, let's go back to being 2-dimensional, because then we can draw things. Imagine now that you are a 2-dimensional being in this plane, you live in this plane, and I am a 3-dimensional being, and I take a 3-dimensional cube, like this one, and I project the shadow of it on your surface, on your space, and then I turn it around. What you see is a sort of mess, because you don't see that all sides are equal and all angles are square. You see like some lines of different length and different angles that move around, and you wonder, what is that? For me, it's very easy. For you, it's very confusing. So what would it look like if a 4-dimensional being took a 4-dimensional cube that for it would be very easy, very simple, project the shadow in this 3-dimensional space and rotate it? Well, we would see something like this. This kind of, it looks like an impossible figure for us. It's really confusing. And we cannot see that all sides are equal and all angles are straight, but we see this kind of very weird shape. But in this, if Cooper is in one of these objects, he would be in one of these. Now the faces are actually cubes, so he would be in one of these cubes, like this. And the room would be on the other side, like intersecting the room. But it's the same idea. If he looks up, he sees us from above. He looks down, he sees us, and so on. And this is, more or less, this is what he would see. Okay? But they add also the extra possibility of being able to move in time, because there are beings that can control also time and so on. And then he can move in the diagonals. He moves through time. And then he's there with the robot. The robot is nearby somewhere in like a different room, let's say. But they can communicate via radio. But then there is a thing that there is the issue of how does he communicate with Murph? Because he can see Murph, but Murph cannot see him or hear him. The interpretation to this that they give is that actually the cube is placed, because it's a space-time, the face where Cooper is pointing to the future of Murph. So all information can go towards Cooper, but it cannot come back. But then at some point in the movie, this is something that apparently Christopher Nolan likes to do. He gives like the rules of the universe in which the movie is going on, the movie is happening, and he acts. I mean, all the story must be consistent with those rules, even if those rules are not really based on physics. And this is the same here. When they are in Miller's planet, Cooper is very concerned by the fact that many years have been wasted, and he says, "Okay, there must be a way to go back, to get back all those years." And the girl Brand says, "No, there's no way. The only thing that can come back in time is gravity." Okay, those are the rules that they decide for the movie. It's not based on anything that I know about, but this is what they want to be consistent with. So now the only way that he can communicate with Murph is gravitationally, and that's why he was actually the one that was provoking all these anomalies in the gravitational field. And finally, he realizes that he can use the hand of the clock to communicate all this quantum information to Murph, and then Murph with that can solve the equation, and finally they can use Plan A. So they simply deactivate Earth's gravity and take everyone off the planet and save them. So that's it. I hope you have understood more or less the movie now.
Thank you very much. Yeah, it was a very interesting talk, and I did actually understand more about the movie. And we are ready now for taking questions. Here also, Iro will help us maybe in some cases to answer to the questions. So who wants to begin? Yes.
No observations on wormholes, right? No observation on wormholes. Will there ever be?
I don't. I mean, not that I know of, and I don't think so. I don't know what this negative energy density could be, but I don't think so.
Iro, do
What's
you
your
want to
opinion?
comment on perhaps or say something?
Well, yeah, okay. Yes.
Or also your impressions on the movie.
Yeah, okay. It is quite nice. So it's very sentimental, I thought. So but anyway, so it's yeah, it requires an exotic matter, and actually, I didn't know that Kip Thorne has somehow thought that the wormhole will be a so-called Ellis wormhole or Ellis drain hole, as he calls them, really. So, which really requires some exotic matter, so negative energy, and very special kind of, which does not exist. Okay, we can somehow theoretically, mathematically create that kind of matter with special fields, so special. We can build up such kind matter, but there's no observation of that. So in real physics, that doesn't really work. So confirmed physics, so it says. But of course, but the comment about that that I'd always, and first I have seen this film 2 times. So, and after the first time I thought that actually the wormhole is not the Ellis wormhole, but the wormhole which can be built up with 5 or more dimensions, which doesn't actually require exotic matter. But okay, yeah, okay.
Actually, a comment on that. It's actually true that in these extra dimensions, the idea of the movie is that when we in the future know enough physics so that we can leave the brain, and then we do actually have enough control over all the fields outside the brain as well, for us to be very easy to create this, say, wormhole by controlling the fields outside.
Yeah.
So that's a little bit the idea, yeah. So it doesn't, from what I understood, it doesn't require that in our brain there is a negative energy density, so coming from our own brain, but it comes from the outside. So
Sure.
from the
But it's still a question of existence for negative.
Yeah, of course, yeah.
Some exotic matter.
Okay, but in any case, I think, I mean, I don't think there were any wormholes was ever observed independently from the type. I mean, whatever, yeah.
Actually,
It's funny that we have this. It seems that because we have this only for recording, and okay, never mind.
yeah, there's are wormholes in a theoretical way in simple general relativity. So it's called Einstein-Podolsky-Rosen. Einstein-Rosen bridge, not Podolsky, but it's a different thing. But unfortunately, they are not traversable, so it can't go through.
Also, there is one thing about the current solutions of wormholes is that they allow time travel. They allow for time travel to travel back in time, at least to when the wormhole was first created, and that's a big issue because of causality, and that's one of the reasons why it is believed that a traversable wormhole shouldn't be possible. So it's like from what I understood, it is taken as one of the limitations of the theory that should be solved by a quantum gravity theory.
Okay. Yes.
Thank you. See, it's nice to think and in fairly short time to build a human colony on the surface of Moon and possibly on Mars. And possibly someday transfer there 1,000 people. But to transfer there 1 million people, let's forget it. Let's solve the problems on the globe, right? We must put all the efforts and money there. It's nice to consider these things, but the practical use is useless. And let us not speak. There's no worth of speaking and considering to traveling to stars because of the huge distances and the time needed to that.
Yes. Maybe Iro can.
Yeah, exactly what he was saying there before me. I think the main message in the movie was this word "stay." This word "stay." I think that's the main message of the movie.
Okay. Yes. Maybe you can just pass it. And
Yeah.
yeah, exactly. That will be easier.
So one of the main devices at the end of the movie is this idea that he can somehow use gravity to communicate with Murph. But it seems like there's no description of how that could possibly happen or what mechanism is used. Is there anything about that in that you know about?
Not really, not that I know of. This is basically it's just for the script, let's say, but it's not like based on anything particular. Actually, closed time-like curves. That is meaning going back to sending information or acting on the past. It's a in the end it reduces to a logical problem. It's difficult to think of a theory that can actually allow that to happen, right? I mean. That's also my personal opinion, but
If there's no one else, I have a follow-up question, which is that you talked about causation, and it seems to me that there's one of the key problems with the movie is that when Cooper is describing to himself how to get to the NASA base from within this square thing, he's doing it from a position on a timeline where he's already traveled. So that seems crazy. That seems like it's fundamentally wrong that he would have had that couldn't have happened.
yeah, exactly. That's what I mean. If he then decides, no, I'm not going to do this, then it's impossible. It's logically inconsistent. Logical inconsistence. Actually, in this movie, I think it's that I know of. It's the only movie in which you have this sort of affecting the past within a story of affecting the past.
Yeah.
So the past. So humans in the future act on their path, on the past, by putting the wormhole and so on, and then in that past, humans affect their own pasts. So it's a loop within a loop. It's actually,
it's
I think, it's
infinite recursion.
yeah. I think it's the only movie where I've seen that.
More questions? Yes. Can you pass back?
I don't know if I need that. I have strong voice. Okay. Yeah.
It's just for recording, for the video. It's not for.
No.
It's not amplified. But
Yeah. Just out of curiosity, you were talking about those gravity waves. I don't know much of them. They're quite new thing. And you were talking about that if we would go to a fairly stable wormhole, it would feel nothing. But then again, you were talking about those they could pass perhaps those gravitational waves the wormhole. So if they pass and people would be able to go through, would they change the feeling? How they would feel.
So you mean, I don't know if I understood correctly. So you mean what happens if you pass through a wormhole in which there's gravitational waves passing by?
Yes, exactly.
Well, I guess in principle, if you could detect gravitational waves somehow, you could detect them as you pass the wormhole. But in general, they are difficult to detect, and you need very large devices, not evident.
Okay, so you would say that it's like the same thing
Ido
that you
should
would,
answer that.
yeah, that it would be the same thing that you would recognize them being right here. It wouldn't change.
Okay, I'm gonna leave this to you.
So usually the gravitational wave are so weak that we can't observe, but with very delicate instruments like LIGO or something like that. But of course, if the gravitational waves are very strong, so deformation of the space-time are really large, so to say, you can maybe, think that you could observe such effect as the shake of the ship or spaceship or something like that.
Yeah, that was what I was
Yes.
thinking about.
It would
If
be possible,
it
yes.
gathers them from the large area, and
Yeah.
like in a way like amplifies them going through the tube or something. Okay, thank you.
One behind. Yes.
Hi. I was wondering if Kip in the book talks about the planetary system around the black hole. So I could see in the diagram he needs like a 0.99 C rotating Kerr black hole, and then he puts a planet at the closest stable orbit, and presumably the planet doesn't get cooked by the solar temperature accretion disk. Does he look into whether that's possible to have this like normal kind of pretty pleasant planet that close to the black hole?
Yes, I think so. I mean, I really think he took everything into account, and actually this 0.99999 C spin, he realized that there is it was discovered by himself that there is a limit to how fast a Kerr black hole can spin, and for the requirements of Christopher Nolan, it happened to be like slightly below that limit. So it was a coincidence, I guess, that Christopher Nolan wanted those numbers, but in principle, it's physically possible. Although he also says that it's it's highly unlikely to find a wormhole, a black hole of that sort.
Okay.
More questions? Yes.
Yeah, so what is it known what was the personal motivation of Kip Thorne to go through all the work of calculation and making the script, and why did he do it?
Well, I don't know why he did it, but my guess is that he couldn't avoid it. I mean, he needed to do it. It's his field, he knows it, and I guess he wanted to make it right. And also, it turned out, like, from this movie, he was able to publish afterwards 2 papers from the visualizations, because these visualizations of the black holes that he got from the FX people, for him, he said, it's like seeing them. So it's like being in a lab outside in space and looking at them, and he realized that the orbits, he realized things about the orbits around the rotating black holes that he didn't know, and he published them. So it seems like it was worth it for him.
But originally, did he write? So you were saying that he wrote the script first, and then it was the original one. So, but it was somehow he had an idea of he wanted to have a movie on this thing. Okay, but it's not known how much it's they overlap with. Yeah.
Well, yeah. Well, I don't have a question about black holes, but and maybe it's not even a question, but annoying observation that I just noticed that they leave the Earth with a regular three-stage rocket, but when they are passed to the wormhole and investigate all these new fascinating worlds and planets, suddenly they don't need three-stage rockets. They have this magical space shuttle they used to travel, and still these planets are supposed to be size of Earth. So I was, I don't know if this is a question. I just
I think that's a very good observation, and I guess, for example, when in the Apollo missions, it also, in a way, it happened also that they didn't have these very big rockets to leave the moon. But of course, the gravitational pull of the moon is a lot lower than on Earth, and also there's a thing with the atmosphere that. It's one of the things that makes it very difficult to leave Earth is that if you want to accelerate, you find a force that is proportional to the speed at which you are moving, which is the one that the atmosphere causes. So I don't know how is it in Miller's planet or in, but of course, it's an issue, I would say.
Yeah, well, actually, maybe I was thinking that if you have read the Kip's book, maybe he talked about something about that, but apparently he didn't.
Not that I remember. Maybe he does, and I don't remember. Could be.
So maybe there are no more questions. Usually, at the end of the Science Cafe, we have extra time to talk with the speaker. Now, this is a new situation. I don't know if we have extra time. So I also don't have any idea what time it is, actually. 7:30. So definitely we have no time. So, but 6:30, we have time. Okay. Yes. Yeah. You can, if you want, we will be staying maybe a few more, 10-15 minutes or half an hour, because we have time till 7. So if you want to ask more questions to Guy, you can do it, and of course probably have a beer or something. Before thanking Guy again, no, first we thank Guy again, and then I have one more thing to say. So thank you again. It was very, very nice talk. So we will be back next year with Science Cafe. We will announce the new lineup of speakers soon on Facebook. We already have agreed a new series of Science Cafe events starting from January, once a month. And because it's the last one, obviously, I would like also to thank very much for the help in running the Science Cafe, Boris, who is there, and who is doing a lot of work. He is the author of all these fantastic posters that you see of the Science Cafe, and also of all the videos and the beginning part of the videos, and really takes a lot of time. So thank you so much. And also Tula over there, who helps me a lot for organizing and finding the speakers. So thank you, Tula. I think we will see again next year in January, but please stay a little bit and have a chat with Guy, who is here. And thank you everyone for coming. Thanks. Oh, sorry, we have to thank Iro, who was our panelist here.
Yeah, sure, that's right. It's about saving your own story. Sure.